Welcome to today's edition of Weather or Not. I'm Meteorologist Brian Karstens. Well, on today's program, we're going to explore the world of weather, and we're going to do this a little bit differently. We're going to actually go back to weather school today. Now, a couple of thoughts about this. First of all, those of you that know me may know that I actually have done several weather classes over the years, mostly with middle school age students. I've done weather camps. I've done, oh my goodness, so many weather experiments. I couldn't even begin to name them all. What the tornado, I love that one. But anyway, education is one of my really big enjoyments. I love to teach people about weather. So today's program, we're going to go back to weather school, and you're never too old to learn about weather. And I think it's an interesting topic because many of us see things on weather, and, you know, sometimes we try to do our best to explain various concepts about weather, but, you know, we don't always have a lot of time to do that on a normal television broadcast. Might have 3 minutes, maybe 4 minutes to do the weather. So to go into a little bit more detail, I thought this would be an interesting subject today. So we're going to cover as much as we can about some of these core subjects of weather. So the next time you see these maps, maybe it'll give you a couple of more insights into what we observe. So the first topic today, real basic one. Why do we have weather in the first place? Good question to ask. You may not have thought about all of those kind of things before. So we'll tackle that. We'll also look into the jet stream. Most of you hear us talk about the jet stream, but we don't always explain why there's a jet stream and more of what it causes. Also, the basics of storm systems. When I say that, I'm talking about low pressure, cold fronts, warm fronts, a little bit more about just some basic things to think about. And as time allows, we'll also intertwine the subject of wind. Oh, yes, wind on the prairie, no shortage of that, usually not for long. Okay, so let's begin with a quick lesson about the weather on planet Earth. Now, of course, here's a little interesting tidbit you may not have known about. I taught a class on astronomy 2 years ago. That's a whole nother discussion. I had a lot of fun doing that. I had a bunch of high school students. And in the process of teaching astronomy, I learned a little bit about the weather on the different planets. Earth, different, very different from Mars or any other planet we could name. So I'm not going to go there today. But just to let you know, I have studied that. So on Earth, okay, a couple things we're going to look at. There's our planet Earth. Now, this map here, this is the what we call the 500 millibar pattern. Okay, so you're saying, Brian, wait a minute, what's that? Okay, all you need to know is this is basically looking at the mid-levels of the atmosphere, and we're looking at the colors representing areas of higher pressure and lower pressure. Okay, so blue, purples, this is low pressure, or actually, to be honest, this is actually colder air reducing the depth of the atmosphere. Now, let me ask you a question. What causes weather? Think about that for a moment. What causes weather? Well, first of all, we got to start with the sun. Sun is heating the earth, right? So we look at the equator. Go all the way around the earth. Go all the way. You can go anywhere, obviously, along the equator, and you will find the warmest regions on the planet, right? Sahara Desert. Talk about the tropics. We talk about the Amazon rainforest, the Congo. This is the heart of where we get the most direct sunlight. Well, also, we know on the flip side of the token here, we go to the poles, the polar regions, North Pole or South Pole. This is the area that receives the least amount of direct sunlight. So temperatures are colder. And what's going on here in a very broad sense is that the energy that hits the Earth is trying to redistribute. So all that heat from the equator, okay, it's trying its best to flow northward. And so what we get in the process of that is a whole bunch of things. And it makes our area interesting because, as you know, South Dakota, KELOLAND region, we are about halfway between the North Pole and the equator. I don't know if you knew that or not. If you ever pay attention to look at your maps, look at your degrees latitude on a map, and we're in that 40s range, right? So we're pretty close to the halfway point. And so we're in the exchange zone. We go back and forth. We get warm. We get cold as all of these things are changing. Now, I could go back another step here, talk about the seasons, obviously the tilt of the earth and all of those things. But for today's discussion, we notice that we have a lot of moving parts to the weather in the northern hemisphere. Look at all those little lobes of low pressure. Here's something really interesting. Let me do this. I'm going to click this open. Okay, so this is my editor function. Okay, so let's zoom back out. Now let's look at this over time. What do you notice? Do you see that? All those little areas of waves that go back and forth, back and forth. Well, it turns out on planet Earth, and this shouldn't be a surprise, but different areas of the Earth heat up at different rates, or basically looking at land versus water. We look at northern regions versus southern regions. There's always disparities or differences in heating and heating rates. And so when we look at the differences in how air heats or consequently cools, it creates pockets of wind because that create that unevenness, if we want to say it, of the Earth's temperature is actually the root cause of wind. Okay, and then just to expand it a little bit more, that ties into this whole subject about the jet stream. Now, these arrows, see all these that are kind of moving around like this? Okay, so this is my basic representation of how the winds in the mid-levels of the atmosphere work. But it gives us some ideas on how storm tracks will go. Usually these larger areas of low pressure and high pressure kind of follow the rhythm of those things. And notice, too, the peaks and valleys. Lots of those, right? Now, you ever stop and think for a moment how complicated this is? Isn't it a miracle that we actually have technology today that actually can look at this and we can get a sense of weather? Certainly the first 7 days, we can usually identify a lot of these things. Not always. Some patterns are easier than others, but depending on what time of year it is, that can, make a difference. Usually in the transitions between seasons. Spring, or let's say winter going into spring, that's tough. The other way is true as well, going into winter. Sometimes the modeling doesn't like to handle that as well, but it does give us an idea of the complexity. Look at all of that complexity over the entire Earth. And to think that we have weather models now that run and crunch numbers on where these patterns will go, honestly, every hour we have models that come in. We have long-range models that are doing things on every 6 hours we get a 10-day forecast. When I started at KELOLAND many years ago, a few of them anyway, about 25, we didn't have any of this stuff. This is way beyond the scope of what we had at that time. And so as a meteorologist and as you entertain these concepts, it gives us some ideas of just where we're at, where we've been, and where we could go in the future as we learn more about this. So that's just a basic overall view of the planet and the Earth. Now, coming up next, we'll dive in a little bit more into weather school today. We've got some more topics of conversation. So that's up next. Stay with us. Welcome back on this edition of Weather or Not. I'm meteorologist Brian Karstens. Okay, Weather School continues today. We're going to talk about some more applicable things of weather. So when we see these daily weather maps, this is going to help us explain a little bit more about how things work in weather. So the first map up here, okay, we're going to talk about the different air masses that affect KELOLAND. So there's a lot of abbreviations, a lot of things on this map, but I want to talk about those. So the first, when you look at the central part of the United States, there's a C and a P. Do you see that right there in the middle of your screen? So that represents continental polar air. That's another fancy name for air that comes out of Canada. Okay? Yeah, Canadian air can be, typically it's a little drier, really dry in the fall or other parts of the season. We typically don't see a lot of moisture from Canada, but it originates on the continent of Canada, so at times it can be warmer. Much of the time we think of that as being colder weather. Now, there is a cold front right in the middle of your screen, that blue line with the little blue barbs on it. That's what we call a polar front. It just means that those air masses are arriving from that polar air mass or the continental polar air mass. So again, those are things that we think about more so in the cooler seasons of the year. Now, of course, in the summertime, we don't think of that as much, do we? We think about other air masses. Like, for example, do you see the letters MT? Any guesses what that means? MT. That stands for maritime tropical. Maritime meaning from the sea, right? From the ocean. And the T for tropical. So that's where we get that abbreviation. And there's obviously the effects of the Gulf, the Atlantic Basin. That's where a lot of moisture. If it weren't for that, we would not be growing crops in KELOLAND or South Dakota. We have to have water. It has to come from those areas of the earth. So that's what feeds in here during the spring and the summer and, a little bit in the fall as these fronts are going back and forth. CT, do you see that in the middle of your screen? That's continental tropical, so that's your desert, that's your heat. That expands and contracts, it moves around, it kind of dances back and forth during the summer. Sometimes when that gets closer to us, then that's when we get 100-degree weather or something like that, 90s, 100s, all the warm and hot weather. As the seasons cool, then that goes right back to Arizona, goes back into those areas. But we know it's drier, obviously, as you know, the weather patterns there. Others of these, they don't affect us as much, except for that CA way at the top. That's our Arctic air. Yeah, those are the big fronts that come through in the middle of winter. And they're definitely a factor, aren't they? Okay, so air masses, right? Different air masses have different characteristics. That adds to the conversation about temperature differences. And when you factor all that together, we come up with the concepts of high and low pressure. Now, high and low pressure, some things to think about with this, okay? When we talk about at the surface level, and this is a broader view of high and low pressure, but remember a couple things. First of all, air motion. What is going on with low pressure? Air is rising. Do you see the arrows, the red arrows? Okay. Air that's rising gives way to clouds, precipitation, so that can look like rain or snow, depending on the time of the year. High pressure, the opposite. The way that the weather works, high pressure leads to sinking air, so we expect fair weather conditions. And also, very important that we acknowledge the fact that the air is circulating around those areas of high and low pressure differently. Now, I'll add another thing here. Notice the arrow. We have H for high, L for low. We've seen that many, many times, right? Over the years. We show these all the time on weather maps. But remember, air is moving from high pressure to low pressure, as this arrow shows. Now, stop for a minute. Think about this. Why is it that when the wind is blowing, okay, think about this. We see this all the time. We talk about what? Low pressure, counterclockwise winds, right? And then around a high pressure, it's the other way. I think my next graphic actually shows that a little bit better. Let me see if I have that. I know I had a couple of these. Here we go. Right here. Okay. See that? Got arrows moving one way around the high. Arrows are moving the other way around the low. So why do we not see wind just going direct? Doesn't that seem logical? It should just go right from the high to the letter L. Not so fast. Remember, what do we know about the planet Earth? Well, it spins, doesn't it? It rotates. So, rotating the axis of the Earth, the air, yes, I know, it's going from high to low pressure, but there's an apparent force at hand. It's called the Coriolis force. And so that's an interesting concept. I could dive into that one for a little while too, but for today, I'm not going to do that. But at any rate, just know that air, it has the apparent deflection as the Earth underneath is rotating and moving. The air that's trying to go direct from one point A to point B, it doesn't really do that. It deflects or curves. And I've got some weather experiments. If you want to know about that a little more, see my email there, bkarstens@keloland.com. I can set you up with a couple of interesting experiments because I've done this in class and it's kind of fun to do. Well, at any rate, getting back to our high and low pressure, let me show you this graphic one more time. So What really happens is that the air mass is going in these circular formations. Low pressure is easy. We see that every storm, every major storm of any significance comes through here. It spins, right? And so that is an efficient way for weather systems. Basically, think about the redistribution of that warm and cold air we talk about. The equator being warmer, the North Pole being colder. These storm systems, and likewise the high pressures that usually come on the other side there, those are the mechanisms that redistribute the energy on the Earth. Okay, so when you see these big storms coming through, all we're seeing is that, hey, there's been some sort of a difference in temperatures on some other areas of the Earth, and now we have to redistribute energy. And sometimes when those things really clash, really get intense, that can create a lot of weather. And we know we can get that here in KELOLAND. Okay, well, that's a little bit of that segment. Coming up next, we're going to visit more about this subject and a little bit more about how storms form. Stay with us. You're watching Whether or Not. Welcome back to Whether or Not. I'm meteorologist Brian Karstens. Well, today's program is a little different view into the world of weather. We're talking weather school today. We talked about high pressure, low pressure last segment. We've also talked about why we have weather. Fundamental question, isn't it? Why do we have weather? Why do the clouds go and do what they do and temperatures go back and forth? So we addressed that subject just a little bit. Now, next segment, we're going to talk about a little bit more about fronts and how storm systems form. We all know, or I've talked many times over the years about warm fronts and cold fronts. Warm front, if we say a warm front's coming in, well, it's pretty obvious. It means warmer weather is coming in. And you can think of it, if you think three-dimensionally, like this graphic implies, that as warm air slides over top, it does lift the air. There's a mechanism here in place to creating clouds. In fact, actually, with warm fronts, we typically have more widespread cloud cover. Also, we tend to broaden out chances of rain. In the summertime, it can be a focal point for severe weather. It just depends on the time of the year what we're actually going to get. But warm fronts, yeah, warmer air is on the way. That's an easy one to think about. Cold fronts, just the opposite. Now, cold fronts, the way they're stacked in the atmosphere, it's a little important that we look at the depth of that blue wedge. Do you see that? Well, cold fronts are sharper. Those are the features, and a classic example, I think of a lot of times when we get a line of thunderstorms in the summertime, or even in the wintertime, maybe we'll get a sharp cold front coming out of the northwest with a really strong push of northwest, brutally cold wind. Well, cold fronts, they tend to be very sharp, and as a result of that, they tend to be a little more vigorous in their nature, that we tend to get more focused precipitation on a line. That's very typical. Now, in the summertime, that could be just a really intense line of thunderstorms and the red and the purple colors on the radar. In the wintertime, it just might look like just a real sharp change in the weather with a sharp cold front and drastically colder weather. Northwest winds typically come in with a cold front. The opposite true with a warm front. Now, if I can just back up for a moment and talk about fronts and storms. Okay, so let's bring up a hypothetical situation where we have what's called a stationary front. That's what you're seeing here on the screen. So on one side of the stationary front, we'll just assume for right now that we have some humid, let's just say, for example, it's warm in the summertime. So you have warm, humid air on one side. The other side is a little cooler, drier air. And this will look different in the wintertime. It might be relatively mild on one side and then sharply colder on the other. But in the process of trying to redistribute that energy between one side versus the other, we get storms. And this is a concept we all see, right? Low pressure forming. And in the progression or the timeline of storm systems, this is the stage one, as I'll say. So you'll get some sort of a wave that'll come along the jet stream and try to initiate this whole process. And So low pressure will form if there's something the upper or mid levels of the atmosphere that causes the air to lift. So once that process gets going, then it starts to pull and bend that front. Do you see that kink in there? Now you got a warm front. You don't have a stationary front anymore because the front side of the low is moving to the north. Then on the back side, as the low begins to develop, it's starting to turn that wind in that counterclockwise circulation, isn't it? And so we get the formation of low pressure. Now, this process looks different every time. If you really want to talk about big, fast developing storms, well, get into the winter months. Maybe November. That actually might even be a better example. That's probably the time of year I've seen the most rapid development of these type of low pressure centers. And it's typically some sort of a clashing air mass. We've got a very vigorous mid-level wind. And so these things, see those lines, those little circles that go around the low? So those are the isobars, the lines of equal pressure. And we talk about the barometer a lot with low and high pressure because we need a way to measure it. We wouldn't have a way to measure it if we didn't have a barometer. So the lower the pressure, the deeper the low. The higher pressure, the higher the number. And if any of you still have a barometer at home, some of you have the automatic ones, and some of you might have the old-fashioned ones. Barometers are not new. They've been around a long time. That was a key instrument back way before modern technology. If the pressure was dropping, we'd say low pressure was moving in, and that would typically signal storms like this. High pressure, just the opposite. Fair weather, drier weather. And it still works today. Nothing has changed with that. Now, what can change or what does change, and I've got a couple other maps here I want to bring up. And this one here, we'll bring into motion. There's the mature stage, okay? So do you notice the life cycle? If we go back to stage 1, stage 2, stage 3, you notice some differences there. Do you see what happens? We'll go back to stage 2 again. There's the low, there's the warm front in the red, the cold front in the blue. And that's a mature storm system at that point. But in this third cycle, do you notice there's another color? A purple color. That's what we call an occluded front. Little terminology for you. So if you see that, that means the storm has basically matured and is actually weakening. It's actually dying away. That first low will get cut off. A second low might develop on the frontward flank of that. And so this process can redevelop again, or it can just sit there and dissipate, and that might be the end of the life cycle. Every situation is different, but key terminology here is that the stronger or the more tightly packed those lines are, the stronger the wind, okay? So remember that, isobars. Yep, when they're tightly packed, the wind is blowing stronger. When they're more spread out, there's less wind. Okay, that has to do with a lot of the math and physics in the atmosphere. But these storm systems, they come and go all the time. So it gives us just a little bit more of a reflection on how that process works. And there's a lot more to it. But I thought for today's discussion, that would be a great starting point. So we did cover wind, didn't we, in that whole conversation. Jet stream, we've covered that, and why we have weather. Well, I hope you learned a thing or two today. As always, if you have a question about something you've seen on our program, feel free to email us. My email, bkarstens@keloland.com. Love to hear from folks about that, and we enjoy visiting about those types of things on our show. Well, that is today's edition of Whether or Not. Thank you for watching, and have a great day.